Hello, welcome back to Calc 2. This is 10.5. We're looking at two types of tests today. The first one we're going to look at is the ratio test. The ratio test basically takes the quotient of the next term and the current term, so namely an an plus 1, so the nth term compared to the next term. If the limit exists, as you put in the ratio in absolute value, then we can conclude this with three things. First, if L is less than 1, then the series is absolutely convergent. If it's greater than 1, or if the limit is infinity, then the series is divergent. And if it's equal to 1, then it's inconclusive. Right. So before we move on, let's talk a little bit about this new term that we have here, absolutely convergent. This is basically um, the definition of it is the sum of the absolute value of the summand is finite. Right. So the summands are basically the numbers that we're adding together. So in this case, an and an plus one, right, or all the ai's. Right. So if we take the absolute value of all the terms in the sequence, and we add them together, if it's convergent, then we say it's absolutely convergent, and it's a stronger form of convergence. Right. So absolutely convergent is stronger form of convergence. Nevertheless, we are still in the conclusion that this series is convergent, which is what we want to show. All right, so let's do an example together first. The ratio test is actually really fun and pretty simple to work with. Nothing too tricky. So first, we need to identify what the an term is. Now it's actually given to us just right here, n cube over 4 to the n. And then we need the next term, which is an plus 1. So we need to write this out. So replace all the n's in here with n plus 1. We have n plus 1 to the third power and 4 to the power of n plus 1 plus 1. All right, and let's take the ratio test. Limit as n approaches infinity of the form absolute value of an plus 1 over an. And let's see what we have. So we have the limit as n approaches infinity, an plus 1, that's n plus 1 cubed over 4 to the n plus 1, multiplied by the reciprocal of an, which will be 4n over n cubed. All right, and let's see what we have. We can simplify some of the stuff first, or we can reorder them around. All right, so I'm going to reorder them around first before I do any simplification. All right, so I'm going to put n plus 1 and n in the same fraction, like that. Right, and since they are n to the third power, right, when we take the limit, this will all go to 1. Right, and the next one I have 4n over 4 times 4 to the nth power. I can rewrite 4 to the n plus 1 as 4, right? That plus 1 tells me I'm multiplying one more 4 than 4n, right? So I can do that. And once you did that, we can simplify these two, 4n and 4n. And the first fraction, that all goes to 1 as n approaches infinity. All right, so the limit that we have goes to 1 over 4, which is less than 1, right? And we say it's absolute convergent by ratio test. Okay. So pretty easy to work with, right? Once you know what to do, basically you put them in the form of a ratio, take n to infinity, and see what the result is. All right, let's look at another type of test. All right, similar to the ratio test, we have the root test, which also tests for absolutely convergent. And the way to do that is we are going to take the nth root of the absolute value of an as n approaches infinity. Right. So same idea. If the limit is less than one, then we say it's absolutely convergent. If it's greater than one, we say it's divergent. And if it's equal to one, the root test is inconclusive. So the setup is a little different than the ratio test, but the result, how we interpret the result, is the same. And then also we have absolute convergent in this case as well, because we are taking the absolute value of an in this case. Okay, so let's take a look at an example. All right, another example: determine whether the series is convergent or divergent by using the nth root test, the root test. All right, so let's go ahead and do that. Limit as n approaches infinity of the nth root of the absolute value of 2n plus 1 to the nth power over n to the 2nth power. All right, so what we can do is we can take the limit as n approaches infinity and everything to the power of 1 over n. And now let's look at inside the absolute value. Now, since n is always greater than 1, inside the absolute value, everything will be positive, right? So in this case, we can drop everything in the, we can drop the absolute value, and we just have 2n plus 1 to the nth power over n to the 2nth power. And then by the power rule of exponent, I can multiply this 1 over n into the exponent in the numerator and denominator. Okay. And then we will have 2n plus 1 over n squared. Okay. And this is very nice, right? We have a linear over n squared. And then when we take the limit as n approaches infinity, right, we have n squared here in the denominator, which grows faster than the numerator. So that will go to 0. Right. Therefore, it's less than 1, right? So we say it's absolute convergent by the root test. Okay, so that's a basic introduction to the ratio test and the root test. And next, let's look at a few more examples together. Now, one question you might have is, how do you know when to use the root test or when to use the ratio test? Now, as a general rule, we use the root test when you have everything to the nth power, to some power, some form of nth power. All right. All right, so if you look at this example, here we have n factorial and 4 to the n. Well, n factorial is not to the nth power, so it's going to be very hard to take the nth root of the n factorial. So in this case, ratio test is actually a better fit because ratio test will work very nicely with the n factorial term. And let's take a look at this together. So we're going to use the ratio test. Okay. All right, so limit n approaches infinity of absolute value of an plus 1 over an. All right, and let's just write everything out. N plus 1 factorial over 4 to the power of n plus 1 multiplied by the reciprocal 4 to the n factorial. All right, and I'm going to do the same thing. I'm going to reorder these around so we can start simplifying. Right, so first I'm going to have the factorials here, n plus 1 factorial over n factorial, and then 4 to the n over 4 to the n plus 1. Right, And let's see what we have. We can start simplifying our stuff. Now, if you look at the first term, n plus 1 factorial has one extra term than n factorial, right? Which is just the n plus 1. Right? So I have, for the first part, I have the limit of n plus 1 left. Okay. And same thing in the denominator, like what we're doing earlier, we have an extra 4 in the denominator. So that gets simplified out to just a 1 over 4 like that. Actually, let me write it to the right. 1 over 4. Okay. And when you take n to infinity, this whole thing goes to infinity, right? Which is much greater than 1. Then we can say it's divergent by ratio test. Okay. So I actually want to go back and clarify a few things. N plus 1 factorial and n factorial. So n plus 1 factorial actually looks like n plus 1 times n minus 1, 3 times 2 times 1, right? And then n factorial is n times n minus 1, 3 times 2 times 1, times 1, right? So we actually have n factorial in here, right? That's n factorial. So n plus 1 factorial can actually be written as n plus 1 times n factorial, right? So when we simplify n plus 1 factorial and n factorial, we can just divide the n factorial, leaving us the extra n plus 1 term left in the numerator. And here is another reason why it's good to use the ratio test when you have factorial, because these type of simplifying happens, right? Where you have that one extra term that will make a difference. Whereas if you use root test in this case, it's probably going to be inconclusive because we have no idea how to take care of the nth root of n plus or of n factorial. All right. So but if you get stuck, maybe let's say if you're using a ratio test and you get stuck, then maybe you can try root test. Maybe it's another way to go, right? We never know, right? And plus, one upside with the ratio test and the root test is they are fairly short in terms of the work that we have to write down, right? So it's not going to be against you if you try both of them. Right? So it's always a good idea to give both of them a try. And sometimes they both will work too. All right, so here is another one for you. Go ahead and pause the video and try this one out on your own. You want to think about which test would you want to perform, right? Which test would you want to use? Okay, so personally, I'll probably use the ratio test because first I have n to the second power here, so nth root the root test is not going to work that well. Plus, I have the factorial in the denominator, even though it's not as easy as the one that we saw before, but factorial is going to work nicely when we use a ratio test. Okay, so let's go ahead and give that a try. All right. And be very careful when you're setting up the n plus 1 part, right? So n plus 1 square, and then in the denominator here, it's going to be a little different. So 2 times n plus 1 factorial, okay? And multiply by the reciprocal of the nth term, which is 2n plus 1 factorial over n square. Okay, and again, let's go ahead and clean things up a little bit. All right, so and then I'm gonna write this as n plus 1 square over n square. Oh, you can see that this is nice, right? It's gonna go to 0. All right, and what about the factorial part? 2n plus 1 factorial. And then this is gonna be, we need to do some sort of distribution here. So 2n times 1, so 2 plus 1, that's a 3, plus 3. All right. Okay. All right. So next, let's do a little work on the side to simplify this thing right here. All right. So let's call this ratios of factorial star and work it out on the side. All right. So I have 2n plus 1 factorial over 2n plus 3 factorial. Now, obviously, the denominator has more terms, right? So let's see what we can rewrite that as. So 2n plus 1 factorial in the numerator. Let's copy that down. Now in the denominator, I'm going to expand out the first few terms. So I have 2n plus 3. The next one will be 2n plus 2. And then the next one will be 2n plus 1. Now notice that we hit the same thing, right? So we can add a factorial here, and then it's going to multiply downwards. All right, so what we can do here is, if we rewrite star as this expression, then we can divide the 2n plus 1 factorial, leaving us 1 over these two binomials in here. All right, so let's go ahead and do that. Limit into infinity n plus 1 square over n square times 1 over 2n plus 3 2n plus 2. All right, now from this point we can see that this, when we take limit as n approaches infinity, the first rational expression here is going to go to 1, right? Because you have degree of numerator is the same as degree of denominator. And then the second rational expression, that's the part that's going to give us 0, right? Because we have a bunch of terms in the denominator, and that whole thing is going to go to 0, meaning our limit is going to go to 0, which is less than 1. Then we can say that it's absolutely convergent by the ratio test. Okay, so you can see that it's not too bad. It's just playing around with factorials, with powers, and taking limits, right? And hopefully this is still not too bad. All right, so I'm going to stop here for 10.5 videos. There will be a lot more practice. We'll look at something that's a little more challenging together when we meet. All right, thank you guys very much, and have a good day.